Hello everyone. Let us continue the fourth problem of continuous beam. So this is the problem. Analyze the continuous beam shown in figure. AB, BC is the beam. So here, to start with this one, first let us open the Staad Pro software by double clicking. So start with the new project. Give plane. Give the name as continuous beam. Fourth one. Check the units. Next, click on next. Then add beam. Finish. Then you select the front view. See the problem, you are having total span length is 5 plus 6 is 11, but here it is the grid size is 10 meter. So edit, increase the grid length by 1 more meter, that is 11. Okay, next. So you should see always X mark to assign the nodes. So first click on 0, so one node is being created. Next click on 5, next is 11, then click on close. So now you can see the line with 3 nodes. So next you have to assign the property general, define. So before this, see the actual cross section. Here he has given the moment of inertia for this beam and for this beam. Moment of inertia you will get by the size of the beam. So here this is I, this is thrice I. So first let us find the moment of inertia. So let us assume breadth as 0.35 and depth as 0.4. Earlier you used to give directly B and D, uniform breadth and depth for the whole beam, but here this breadth and depth is different, this breadth and depth is different, so it is thrice I. So now for this one I, let us find I. So I is given by B, I is given by B dq by 12. So I is equal to, substitute the value, B is 0.35 into depth is 0.4 cube by 12, that is equal to, let's find the value, 0.35 into 0.4 into 0.4 into 0.4 divided by 12. So this is the moment of inertia I value, 0.0018. 0.00186. So next is I want 3I equal to 3 into 0.00186 is equal to into 3. It is 0.0056. 0.0056. This is 3I value. So let us define this one. So define rectangle. Here you can give only the depth and width. So you click on general. So now you can see the here areas ax, ay, az. Ax plus ay will give az. Next, similarly, moment of inertia along x-axis, moment of inertia about y-axis, then moment of inertia about z-axis. Iz is equal to ix plus iy. So you give the iz value. What is the iz value now? For the first one, AB beam, it is I. What is the I value? 0. 0.00186. So material is concrete. Click on add. Next, another one is 0.0056. Click on add. Close. Now you assign this one. Use cursor to assign for this beam. Next, take this one and assign this one. See here R1 and R2 for reference 1, reference 2. Close. Shift N I will press. So to view the cross section, 3D rendering. So now this is general. This is R1. Okay, moment of inertia we have assigned. So it is showing just a line. So next is you have to assign the support, create which are the supports you are having, fixed and pinned. Fixed, create, next pinned, add, close. Fixed it is at the node A. So at the, click on this one. Next, these 2 and 3 pinned are there. Close. Next, you have to assign the loads. This is 100 kilonewton exactly acting in the middle of the AB. Next, this is minus 24, minus 100, and so here click on loads and combinations. Load case details, add, give the name load case 1, add, okay. Load case 1, add. So it is member load. So UDL, what is the UDL is there? Minus 24. So it is minus 24. So it is acting global y-axis. Add. Next is concentrated force. The concentrated force, it is minus 100 acting at a distance of 2.5 meter from this one. This is the D1. Okay. So D1 is 2.5 minus 100. D1 is 2.5. Global y-axis. Click on add, close. So you have to assign this one to this beam. Use cursor to assign. Assign. Click on this one. Next, take this one. Assign also. Close. Next, to see the load, click on this one. Loads. So the scale is very large. So decrease this one. Increase the scale. And to view the value, click on right click load value. Next, scales. You increase this by some 60. I will mention. Okay. Now you can see the load value. This is minus 24. This is minus 100. Even if you want to see the dimension load display. This is 5 meter. This is 6 meter. Next is analysis and print. No print. Click on add. Close. Next is analyze, run analysis. Say. So error should be 0 always. So next go to processing mode. Done. So load case 1. Okay. So already deflection button is on. So view the deflection. So this is the deflection made by the beam. So up to this much portion sagging, this much portion of the beam is going upward, or that is hogging. This is again sagging. So next, bending moment. This is the bending moment diagram. Results, view value, beam results, bending at ends, bending at midpoint, annotate, close. Let us verify the results. Here 53, 55, this is 58. So this one is 54.59, this is 58.54, almost approximate. So this is 77, 78 is there, 68.84, 69.347, 58.54, 58.67, and 54.59 at the. So it is acceptable, whatever the value is there. So it is correct. So let us, so similarly, if you want to see the shear force, this is the shear force diagram. So you click on shear force, click on results, view value, remove the bending, untick this one. Next, click on shears at ends and midpoint, annotate, close. Here 45 is there, here 45.25, here 45.6 is there, here 54.39, 84 is there, 85 and 54, this is 59, 58, so it's the acceptable range. So now let us go for the next problem. So the fifth one, this one, determine the support moments for the continuous girder shown in the figure. If the supports B sinks by 2.5 mm, this support is sinking. For all members, I is equal to 3.5 into 10 raised to 7 mm raised to 4 and E is equal to 200 kilonewton per mm square. So let us start with this one. So go for file, new, again take plane. Next, you give the name continuous B number, fifth example. Next, finish. So you choose front view. The total span length is 3 plus 2 plus 3. 5 plus 3 is 8. So it is within this one. So 3 meter one node is there. Another 2 meter node, 3. So click on 0. Next 3. Next is 5. Next is 8. Next you click on close. So this is 3. This is 2. This is 3. Total 4 nodes. 1, 2, 3, 4. 4 nodes are there. So let us assign the first is the property for this one. General. Here he has given the moment of inertia for the whole beam, that is I is equal to 3.5 into 10 raised to 7 mm raised to 4. So here general, you define the property. So we are not giving the cross section. Instead of that one, we are giving the moment of inertia directly. So it is meter raised to 4 is there. So here it is mm raised to 4 is there. You have to convert that one to meter raised to 4, this value. So 1 mm is 10 raised to minus 3 meter raised to 4. So it is, I'll show this. So I is equal to 3.5 into 10 raised to 7 is there, mm raised to 4, mm raised to 4. I need meter raised to 4. So it is 3.5 into 10 raised to 7. So 1 mm is 10 raised to minus 3. So it is 10 raised to minus 3 whole raised to 4. So it is 3.5 into 10 raised to minus 3 whole raised to 4. It is 10 raised to minus 12. It is 10 raised to 7 into 10 raised to minus 12 equal to 3.5 into, so 10 raised to 7 minus 10 raised to minus 12. It is 10 raised to minus 5. So that is equal to 0.0000035. So this is the I value. So let us give this value. And I is equal to 0.0000035. Moment of inertia, add, close. It is uniform for all the this one. So you can select this one, beam cursor. You can choose beam. So you can assign to the selected beam directly like this. Assign, assign. So you see here R1, R1, R1. So this is the beam cursor I have used for the selecting the beam. So next is E value 200 kilonewton per mm square is there. We'll change it later. So let us assign the support for this. So this is fixed, and then these two are pinned. So support, create, fixed, create, pinned, add. So fixed support at first and fourth, and pinned at 2 and 3. Close. Next, assign the loads and definitions. Load case details, add, give the name load case R1, close, load case 1, add. So this is 40, minus 40, this is minus 100, this is minus 50. This minus 40 is acting over this whole length on this beam. Member load, uniform load is minus 40. Global Y, click on add. Next, this one is minus 50. Minus 50. It is acting over the third beam. Next is this 100 kilometer. It is at a distance of 1 meter from this node. This is D1. Concentrated force. D1 value is 1 meter. That is minus 100. D1 is 1. Acting along global Y. Add, close. So it has been created twice. So you delete once. Delete uniform distributed load. Use cursor to assign for this beam. This minus 50 for this one, and this minus 100 for this one. Close. So increase the scale and view the value, load value. Scales you increase. This one by will increase 70. So you are able to see the load values at the. Next is what is the question? B support sinks by 2.5 mm, he has mentioned. So this support area will be sink by 5 mm. So here general load central definition, load case details, click on add. Sorry, here already on load case we have defined this one. So you choose this one only. Add nodal load is there. This node is displacing by this is displacement by 2.5 mm. See here, this is the nodal load support displacement. It is acting, the displacement is downward, that is minus 2.5 mm. So it is in meter. Minus 2.5 mm means minus 0.0025. 2.5 mm it is. It is acting along y-axis, that is the F1. Add, close. So you choose this one. Use cursor to assign, and click on the node 2. So it will make the displacement of 2.5 mm. Close. So next is you have to change the Young's modulus. That is 200 kN per mm square. So let us see the value. What is the E value is there? Click on this one, Staad editor. Staad editor, this one. So you can see the E value here. It is 217, 2.17 into E, nothing but it is 10 raised to 7 is there. So as you know, the Young's modulus is 2 into 10 raised to 5 Newton per mm square. So it is 2.17 into 10 raised to 7 is there. 2. Let's change this one. So here, let me show you. he has given 200 kilonewton per mm square. So you want the units are in kilonewton per meter is there, per meter square is there. So 1 mm is nothing but 10 raised to minus 3. So it is 200 kilonewton divided by 10 raised to minus 3 whole square. So this will convert to kilonewton per meter square. So it's equal to 200. So 10 raised to minus 3 whole square, 10 raised to minus 6. If we take on the upper side, it will become 10 raised to 6 kilonewton per meter square. So it is 2 into 10 raised to 8 kilonewton per meter square. So this one is 2 into 10 raised to 8. Let us save this one, Control S, or else you can save here, file, save, close. So next is analysis bar print, add, close, analyze, run analysis, save. Next is go to post processing mode, done, load case 1, okay. So this is the deflection. First let us see the bending moment, let us verify the that value, results, V value, beam results, ends and midpoint, notate, close. If you are getting the same answer as of the problem, you have done correct, or else it is wrong. So it is here it is 35.789, here it is 35.77, here it is 17.89, 37.88, 40.928. So I think the done correct. I don't think, but it is correct only. So it is 45.11. So it is 45.2. So 16.67, 16.69. So this is 23.75. That's 743. So here 11.54 is there. Here 11.587. So it is correct, the bending moment diagram. So you know how to take the picture of the bending moment, shear force, and deflection. This is the deflection of the beam. It is reflected like this. Okay. So let us end the class. We'll continue in the we will solve some more problems in the next class.